So I have something interesting to talk about today. So imagine we have with us maybe a disk of radius r, which is, oops, that's not supposed to be a bead. So we have a disk of radius r, and we know that it is rolling without slipping on a flat surface. So what I mean by that, this is a disk of radius r. We know its center of mass is always traveling along this line parallel to the ground with a constant speed and uniform velocity v. And because it's rolling without slipping, what that further implies that about the center of mass, this rigid body is rotating at an angular velocity omega, and the relation between v and omega is v equals omega times r. And now, here's the question that we want to ask. What if we focus on a point which is on the circumference? So maybe let's focus on the point which happens to start at the point of contact between the disk and my ground. And then, after some time, the entire disk as a whole moves to the right. But the point also, with respect to the disk, maybe moves clockwise at an angular displacement along the circumference. And then the question that we want to answer, we know that this guy here, if we keep on focusing this guy, as a function of time, this will trace out some shape. I don't know what that shape is, but this guy will trace out some shape on the xy axis. And I can label my axis, x axis being parallel to the ground, and the y axis perpendicular to the x axis. And I want to find out what precisely what the shape is. I want to characterize the shape. So, what do I mean by characterize the shape? What I mean is, I have with me a set of coordinate axes, so my x and my y axis, and I know this point which starts here at t equals 0. Sometime later, by virtue of the fact that the entire rigid body has moved towards the positive x direction, it might come at some x value here. But because of the rotation about the center of mass, it might have rotated and maybe come here. Same thing again after some, so this is at some time instant t1 more than 0. And again after some time t2 more than t1, the same thing happens. This guy again moves towards the right and rotates, maybe comes here. So at some point of time, it will reach the apex. And that obviously that apex, the height from from the ground, has to be 2 times r. And that's the time when the entire disk has made half a revolution, or rather half a rotation about its center of mass. And that point we were considering is at the top. And what do you think will happen? Well, it's actually going to be a symmetric picture. So it's going to come down here again. It's like we're just playing a replay button. And this here, this time instant, some later time instant, t3, maybe even greater than t2, is the time when we come back to our original snapshot. The disk has made one entire rotation about its center, and we are back to where we start. And what do you guess will happen as time progresses? As time progresses, we'll end up tracing the same shape. And this is exactly the shape we want to know. This is the shape we want to characterize. And by characterize, we want to know what are the x coordinates as a function of time and what are the y coordinates as a function of time. In other words, given a time instant t, I should be able to locate my point on this curve. And that's exactly what I mean by characterizing this curve. In fancy literature, this curve has a name. It's called the cycloid. And we want to be able to characterize the cycloid. So the reason I chose this particular problem is because I want to emphasize the power and elegance of a very versatile mathematical tool, and that's complex numbers. So I'm going to assume the following information about complex numbers. So a complex number is just a represent for our purposes. We're going to just Assume that the complex number is just a way of representing points on a 2D plane. Instead of the x axis and the y axis, we have the real part of z and the imaginary part of z or z. Z is conventionally taken as the variable of choice for denoting a complex number. I'm also going to assume we know this that any complex number can be written as a plus bi, where a and b are real numbers themselves, and I is just the so called imaginary number, the square root of minus 1. Another assumption I'm going to make, by the way, these are assumptions about our knowledge, not just assumptions about complex numbers. So, another stipulation, another fact we should know about complex numbers going forward is that the same representation of complex numbers can also be written down as some positive constant a times e to the I theta. What this means pictorially, this is the complex number z that we're interested in, where a and b happen to be the real and the imaginary parts, which we saw from the first representation. This length happens to be a in the second representation, and because it's a length, that's why it's a non-negative number. And this angle, the angle measured from the positive x-axis, or the rather real part of the axis, is theta. And it's again not difficult to see that a times cosine of theta is small a, and a times sine of theta is small b. Okay, so now armed with this information, we want to start our journey of characterizing the cycloid. Now, this is what we're going to do. At time t equals 0, our point was here. It had real part 0 and imaginary part 0. At some later instant of time, maybe this instant of time, we know that our point has come here. So, rather, maybe this is going to be a bit awkward to draw. I'm going to assume it come here. So, the approach that we're going to follow is the following. I will first locate the center of mass, and that will be given by the complex number z center of mass. And then I will, with respect to the center of mass, I will locate the point which has traveled a distance, angular distance theta. This point, with respect to the center, is the complex number z sub r denoting the radial direction. And finally, adding these two complex numbers, which again for our practical purposes is just like adding two vectors. That's how complex numbers are also added. They follow the triangle law of addition. So that addition gives rise to this z, which is the complex, which is the general trajectory of this point. And as time, by the way, these are all functions of time. Because as time progresses, these complex numbers in general will change. They will change their magnitudes. They will change their angles, their directions. And as a result, this will be z of t, the complex number sum of these two complex numbers. And that, decomposed in its real and imaginary part, will give us x of t and y of t. So let's see. So I think it's pretty straightforward to calculate or even write down an expression for ZCM as a function of time. So what do you think that is? Well, along the x-axis, rather the real part or the real axis, in time t, we have moved v times t. So the small a here happens to be vt, which is exactly this distance. So we got the real component of ZCM. And what's the imaginary component? Irrespective of time, it's always the radius. So to get to this point, we travel v times t along the real part and r units along the imaginary axis. So it's pretty straightforward to compute ZCM of t. Now, what about z, the radial direction, z in the radial direction? First of all, we need the a, the modulus, the so-called modulus or the length of this complex number. Again, that's independent of time because this is always the radius of the disk. So we will now use the second representation. And now is the interesting part. What is theta? What do I write theta as? By the way, this theta here was the angle that the complex number made with reference to the real imaginary real axis. So if you look at this figure here, and I'm going to maybe zoom a bit here, this is my point. What's the angle that it makes with the positive x-axis? And this happens to be the imaginary axis. Can I say that that is three right angles minus a theta? The angle it makes from the positive x-axis or the positive or the real part of z is three right angles, 1, 2, and 3, and subtract the last theta. So let me just go ahead and write that. So it's three right angles minus, I want to write the theta, which is this guy here, but I will use the fact that this angular displacement theta, because of the pure rolling condition, is nothing but the angular velocity times the time. And now we know what z of r is. And then I can even expand it and write it down as r times the cosine of three right angles minus pi omega t plus I, again an r times the sine of the same thing. And now we just add, again by add I mean add in terms of the complex numbers. So by adding complex numbers, we get the x of t, which is just the sum of the real parts of these two complex numbers. And what does that happen to be? The sum of the real parts is, well, again, this v, let me write it as r times omega because of this pure rolling condition. So if I were to do that, I get r times omega times t plus this guy. But what is this? So this is the cosine of something here. And maybe I can write it in a better way. Cos of this is just sine of this. And that's a standard trigonometric identity, and I'm not going to prove this. Similarly, for y of t, we can add up the imaginary parts. So what's the imaginary part? Well, it happens to be r, the contribution from ZCM. And from here, again, it happens to be minus r, cosine of omega t. Another standard trigonometric identity, we're not going to prove. Sine of three right angles minus some angle always happens to be negative cosine of that angle. And there we have it. Oh, by the way, let's quickly do a sanity test and see if this indeed looks correct. Where was our point at time t equals 0? It was at x equals 0, y equals 0. Let's plug in time t equals 0. At t equals 0, x of 0 is indeed 0. What about y of 0? Well, y of 0 also happens to be r minus r times 1, which is 0. Looks good. And there we have it. X of t, y of t, characterized neatly, elegantly, in just half an A4 sized sheet. And this is a very powerful way of working in 2D planes using complex numbers. And this is just one of the ways in which the complex number methodology of representing points on a 2D plane helps us. And I found that it usually help us when we are dealing with things like rotations, because this property of this, rather the second representation of the complex number as this, the angle here takes into account any rotations, so-called rotations in our problem. So here we have it, x of t, y of t for a cycloid characterized pretty straightforwardly using complex numbers. Hope you guys liked it. Thank you.